So in this 23-1 lesson video, we're going to be looking at series circuits and parallel circuits and the mathematics behind that. And in this first slide, you'll see this is a circuit, and in this circuit, these resistors are in parallel, and so actually sometimes resistors are in series. And we're going to look at how to handle that mathematically. So our first question is, well, how do you draw a series circuit? When drawing a series circuit, there is only going to be one loop in the circuit. We draw the power supply. It has this symbol here, and we know that the left-hand side here is the positive and the right-hand side is the negative. And we'll draw our loop, and we'll draw our resistors, whatever number of resistors we have to draw. I'll draw 3 here. And you'll see that it's just one loop, and we can label this R1, R2, and R3. Typically, you'll label the power supply as V, or V total, or E for EMF. And you'll see for a series circuit, there is only one loop. When the current leaves the power supply on the positive side, it goes through each resistor. And you'll notice that the current through each resistor is exactly the same. So one of the important ideas in a series circuit is that the current through the first resistor is equal to the current in the second resistor, which is equal to the current in the third resistor. The current is the same for all 3 resistors, which is also equal to the total current coming out of that power supply. Now our next part here, number 2, says, how do you calculate the equivalent resistance of a series circuit? Well, you'll see here we have our series circuit. There's only one loop. We have 2 resistors in series, and when you calculate the equivalent resistance, you simply add up the two resistors, R1 plus R2. In our reference tables, we have this equation here. We have R series equals summation of all the resistors, all of them, summing them all up, and we'll do an example. So let's say we have this circuit here. We have 3 resistors. Our first resistor is 5 ohms, second resistor is 3 ohms, and our third resistor is 2 ohms. And what we would do to calculate this resistance for this series circuit is we would add R1 plus R2 plus R3 to come up with our total of our net resistance of 10 ohms. So these 3 resistors here will actually act like one 10 ohm resistor would. Quite often, Christmas lights are in series, a series circuit. And if one of the bulbs goes out, all the bulbs go out. So for example, if we go back to this here, if you have one of these bulbs go out, this circuit stops. The current no longer will flow. This acts like a switch. So a lot of times Christmas lights are in series. If one bulb goes out, they all go out. The next type of circuit we want to draw is a parallel circuit. Now, a parallel circuit is the type of circuit you'll find in your house. You can turn off one light switch in your house and all the lights in the house don't go out. And that's what's nice about a parallel circuit. So the parallel circuit allows all the resistors to keep running if one resistor is turned out or if one light is turned out. So let's draw a parallel circuit. You'll have the power supply here. And you'll have one resistor here, and it'll look like a ladder. Another resistor here, and another resistor here. And here's our voltage. This is your resistor 1, resistor 2, resistor 3. And what's important to know here, it's not the current that's the same in every resistor. It's actually the potential difference across every resistor is the same. So that total voltage from the power supply equals the voltage drop across the first resistor equals the voltage drop across the second resistor equals the voltage drop across the third resistor, and so on, depending on how many resistors you have. And what's interesting about a parallel circuit is that if you add a resistor, every time you keep adding a resistor, you actually decrease the resistance of the circuit. And the reason why this is you just added another lane. You've added, this current now has 4 lanes. We're only used to have 3 lanes to travel, and now it's 4 lanes to travel. It's similar to the idea on a highway. If you only have a 1-lane highway and there's a lot of cars on it, there's going to be a lot of resistance. But if you add another lane and another lane, you actually decrease the resistance to those cars traveling. So here you've decreased the resistance to electrons traveling or to the current traveling. So with question number 4, it says here, how do you calculate the equivalent resistance of a parallel circuit? Well, it's this equation here. And in our reference tables, it says 1 over Rp equals um, the summation of 1 over Ri and whatever number of resistors you have. So in this question number 4, it says, how do you calculate the equivalent resistance? Well, let's go ahead and do an example. Let's say our first resistor, let's say R1 here. Let's say this one is 10 ohms. R2, let's say, is 10 ohms. Let's just do 10 ohms for all of these. Let's say we have 4 10 ohm resistors all in parallel. So the way you would calculate that is you would say 1 over Rp equals 1 over 10 ohms plus 1 over 10 plus 1 over 10 plus 1 over 10. And so we would just go ahead and add all those fractions up, and that would equal 4 over 10. And what you have to do here is you have to cross multiply this. You would have 4Rp equals 10. And our total resistance for our parallel circuit is 10 divided by 4, which is 2.5 ohms. You'll see the total resistance has gone down. One resistor was 10 ohms, but all those resistors in parallel together is 2.5 ohms. Luckily, the headlights of a car are in parallel to each other, because if one headlight goes out, the other one still stays lit. If they were in series, if one headlight went out, both headlights would go out. But since they're in parallel, one headlight goes out, one will stay on. So if you look at the circuit here, if you take this resistor and take it out, current can still flow in those other 3 resistors. So let's pause the video at this point, and I want you to try this parallel circuit. See if you come up with the answer of what the equivalent resistance of these 3 resistors in parallel will be. So you start off with this equation, 1 over the resistance in parallel. That's the total resistance. That's the equivalent resistance. What we're asking, if all 3 of these resistors they were replaced by just one resistor, what would that one resistor be? And so we have our equation for parallel resistors. So it's 1 over Rp equals 1 over 58 plus 1 over 70 plus 1 over 42. And this one is a little bit tougher to find the common denominator. So what you can do is just in your calculator, just say 1 over 58 plus 1 over 70 plus 1 over 42, and you'll come up with a decimal, and we'll see how you work with that. So just in your calculator right now, just try that out. If you got stuck, just try that. I end up with a decimal of 0.055. But that's not our equivalent resistance. That's equal to 1 over Rp. What you have to do now is, in order to answer what the equivalent resistance in parallel is here, you now have to invert this side. You have to now invert that over. So that means you have to invert this over, because 0.055 is really over 1. And now what you have to do is 1 over 0.055. If you inverted this side, this is really Rp over 1. You invert that side, you have to invert this side. You can hit x to the -1 button on your calculator, hit enter, and you end up with a resistance of about 18.1 ohms. And what that says is if you take an 18.1 ohm resistor, it'll act the same as those 3 resistors in parallel. Now, question number 5 says, how do you calculate the equivalent resistance of a circuit that is a combination of a series and a parallel circuit? And so I have both examples that you're going to have to know how to do. The example on the left, you'll notice you'll have R1 and R2 are in series, and then those 2 are in parallel to R3. And then over on the right, you'll see R1 and R2 are parallel to each other, which is in series with R3. And the way you handle these types of circuits is that you just look at for example, the one on the left, R1 and R2 are in series, so you take that and you find the equivalent resistance of those two, and those R1 and R2 then treat as one resistor, so that's R1 and 2 together, and then that's in parallel to R3, which you have your voltage here, and then those two, then you just find out the equivalent resistance of those two together, and that's those two are in parallel. And then on the right-hand side, R1 and R2, they're in parallel, so you find the equivalent resistance of those two, and then that will then be in series. That equivalent resistance, R1, 2 together, is then in series with R3, and then you just go ahead and add those two together. So we'll just do one example here, and we have our R1, R2, and R3 are all 10 ohms. And the first thing you do is go ahead and look at R1 and R2. They are parallel to each other. And so you would do 1 over Rp equals 1 over R1 plus 1 over R2. And 1 over Rp equals 1 over 10 plus 1 over 10 ohms. And so 1 over Rp equals, when you add those together, 2 over 10 ohms. Then if you cross multiply and solve for Rp, you get 5 ohms. So what that means is that R1 and R2 together are 5 ohms. So these two here act as one 5 ohm resistor. So what you now have is your circuit now becomes just a series circuit with this being 5 ohms and this one, R3, being 10 ohms, and R1, 2 is 5 ohms. And we know that for a series circuit, you then just add them together, and so it would be a total of 15 ohms. And so that would be your answer. That circuit right there, those three resistors together, act as one 15 ohm resistor. So let's do some example problems. If you look at page 757, question number 12, it says that three resistors, let's see, number 12 says, three resistors in parallel have an equivalent resistance of 5 ohms. Two of the resistors have resistance of 10 and 30 ohms. What is the resistance of the third resistor? So the picture looks like this. So we know R1 and R2, but we don't know R3, but we do know the equivalent resistance. So if we do 1 over Rp equals 1 over R1 plus 1 over R2 plus 1 over R3, we have 1 over, they told us the equivalent resistance here was 5 ohms. That equals 1 over 10 ohms plus 1 over 30 ohms plus 1 over R3. And then the rest is just solving fractions. So really you end up with 1 over R3 equals 1 over 5 minus 1 over 10 plus 1 over 30. I'm sorry, that's minus 1 over 30. You subtract that over to the other side. And you end up with a fraction. If you do a common denominator, you'll see that 1 over R3 equals 2 over 30. If you cross multiply, solve for R3, you end up with 15 ohms. Now we'll look at question 17, which has which is a combination circuit, and I'll let you draw that and try to figure that one out on your own, and then you can check the answer here. So to find equivalent resistance in this circuit, we look at the 30 and 45 together that are in parallel. And so if you look at the 1 over Rp equals 1 over 30 ohms plus 1 over 45 ohms, and you solve that fraction, I'll let you go ahead and do that on your own, but Rp, that equivalent resistance, ends up equaling 18 ohms. So go ahead and try that. Make sure you can do that. And so now that 18 ohms now is in series with the 42 ohms. So this resistor over here, now that these two here now act like that 18 ohm resistor there. You have your 42 ohm resistor, and then you have your 40 ohm resistor. And they didn't draw the battery here, but the battery, you'll see these leads coming out, and the battery really is here. So this is not a series circuit. You'll see that this is still a combination circuit. And so what you do next is you combine the 42 and the 18 ohms. And those two together, that's in series, so you add that. So resistors in series, you add the 42 ohms plus the 18 ohms, which equals 60 ohms. And now that's in parallel with the 40 ohms. So those two resistors have combined to give me 60 ohms, and now we have this parallel circuit. So 1 over Rp equals 1 over 60 plus 1 over 40. And if you go ahead and do the mathematics there, you end up with a equivalent resistance of 24 ohms. The last part I'll do in class with you, page 757, number 19. I'll stop there and talk about that one in class.